Hey guys, so now we're going to talk about the first part of the fundamental theorem of calculus. I know it sounds kind of complicated because it's like a mouthful, but it's actually pretty simple. So let's get right on. So here we have that the fundamental theorem of calculus makes the connection between blank and blank, right? So here we're going to relate two different topics in calculus that we're learning. We're going to make the relationship between derivatives and integrals, right? So let's put that right in there. Derivatives and integrals. Which for sure, derivatives are slopes and rates of change, and then when we talk about integrals, are areas under the curve, right? So the first part of the theorem shows their inverse relationship, right? So derivatives and integrals are actually, they have an inverse relationship, right? So before we talked about the integral, we can also talk about it as an antiderivative, right? So we can split it up into derivatives and antiderivatives, or derivatives and integrals, right? So they obviously have an inverse relationship, in which by inverse I mean they just cancel each other out, right? So let's go see how that applies, right? So there's some restrictions to apply the fundamental theorem of calculus, and that is that our function is continuous in the closed interval, and that is differentiable in the closed interval, right? So we have a continuous function, and there's also a smooth function, right? So what it tells us is that g of x is equal to the derivative of the integration from a to x of f of t dt, and that actually means nothing. Like, that actually, like, what am I even saying right now, right? So let's go ahead and actually draw a little diagram so I can tell you guys what that actually means. So here I'm going to have the x-axis, here I'm going to have the y-axis, and I'm going to draw some random curve. I'm going to draw some curve, right? And then this curve is going to go from A to B, right? We're going to have some interval. And then I'm going to tell you that we're going to first take care of this part, which means that the integration from a to x of f of t dt, right? So what I'm actually telling you is that I'm finding the area from a to x of under the curve of t. So under the curve of f of t, right? So we're actually going to call this function right here f of t, right? And the area under that curve from a to x, so we're going to say that x is some random point between a and b. And that area, we're going to highlight it yellow, that area is right there, right? The integration from a to x of f of t dt is right there, right? And then we're going to say that when we take the derivative of the integration, we actually get the area. Okay, so we're going to let this g of x right here, equal to the area, which is equal to g of x, right? So what we're going to have is that if we take the derivative of an integral, we actually get the area inside. That's what we're saying. All right. So how do we even apply that, right? That just kind of makes no sense. It seems kind of abstract. But the only point of this is to show you guys that the derivative here and the integral are going to cancel each other. That's the whole point. But that doesn't even make too much sense at first, so we need to see some examples and actually apply this theorem, right? So from your book and from the different stuff that your professor gives you, this is the main type of questions that how we apply the fundamental theorem of calculus, right? So the most basic, I can ask you, find g of 0, right? In which I give you g of x as an integral, right? So here I'm just going to find g of 0. So what I do is I just plug in 0 into my x in my g of x, right? So that is going to be 0 to 0, because here's my x, of 2t plus 1 dt. And let's think about this real quick, right? Do I even need to integrate here? And I don't, because if I'm going from 0 to 0, right, if I'm not ever moving, if I don't have an interval in my x-axis, right, if I'm just saying that I'm going from a to a, I cannot have an area because I do not have an interval to have a base in, right? I don't have a base. My base is 0, and I can have whatever height it is. That doesn't matter. But if I don't have a base, it's a height times 0, so that's just going to give a 0. So whenever you go from the same number to the same number, the integral is always going to be 0 because we have no base, right? We have no interval to take an integration over. Then the next part is going to talk about how if I ask you to find g prime of 0, right, here's where we actually apply the first part of the fundamental theorem of calculus. So first I'm going to find g prime of x, and then I'm going to plug in 0. So when I'm asking you to find g prime of x, I'm asking you to take the derivative from a, well, in this case from 0 to x, because a is 0, from a to x of 2t plus 1 dt, right? And then now I'm going to erase all this stuff, and you guys are going to see that it's going to look very similar. It's going to look very similar to what we have here. And what exactly does it mean that this whole thing turns into g of x? Well, what that means is that I'm just going to plug in the x. I'm going to plug in this x into my equation. That's all I'm going to do. I'm going to plug in an x into my equation. And that equation is going to be the f of t. So how I'm going to do that is I'm going to cancel out these two, showing their inverse relationship. This right here shows their inverse relationship. And I'm just going to plug in an x wherever I see a t. So I'm going to have 2x instead of a 2t. You guys see how I have a t here? It is now going to be an x. And I'm not going to have plus 1, because that's just what I have. The dt goes away, and I'm just going to call this g prime of x, right? So that is the idea here, that when I'm asking you to derive this function, I'm actually just going to apply the first part of the fundamental theorem of calculus. So it kind of seems too simple, right? The book just tells you, hey, let's just plug in an x wherever you saw a t before, whatever variable they put, right? But that kind of is a lie. The reason why that's a lie, because that only works when you have a constant, down here, right? So that only works when you have a constant as a, or 0, which they're both constants, and when you just have x. That only works for that scenario. So we're actually going to take this theorem, and I'm going to give you a better formula for it on how to apply it. I'm going to give you a better formula for it using, for example, when you have from 1 to x squared, which we still have the lower interval, it's still going to be 1, which is a constant, but the upper bound, the upper part of the interval, is going to be an x squared. So how does it matter if you go from an x to an x squared? And we're going to see that in just a second, right? So the formula we're actually going to use for this, right, that we're going to use for this part is going to be that the integration, the derivative of the integration from a to b, or f of t, is going to be f of b, right? It's going to be f of b times b prime minus f of a times a prime, right? So that means that I'm going to actually just do, I'm going to plug in my b, whatever that is. In this case, my b is x squared, and I'm going to multiply by the derivative of my b by my derivative of x squared, and then I'm going to subtract it by f of a, which in this case my a is the 1, and I'm going to multiply by the derivative of 1, whatever that is, right? So the reason why, I'll discuss in just a second why the first definition is the one that they talk about, because they only treat it when you have a constant in the bottom, and then the second term is going to go away, because if you have a constant in the bottom, this a prime, right, this a prime that I have here is always going to be 0. So we're never going to have a second term, so we're only really worrying about this, right? So we'll just go over that in just a second. So when I ask you to find g prime of x, I'm asking you to find the derivative, the d dx of the integration from 1 to x squared of t squared plus 1 dt, right? So how we do this is that we cancel out these two, but we make sure to replace every t with an x squared, or whatever our interval here it is, right? So we're going to have x squared. So we're going to have x squared because we have t squared. So we're plugging in x squared into t, and then we have to square that again, plus 1, right? And that takes care of the first part right here, which is just our f of b. I just plugged it into my f of b, and then I'm going to multiply by my b prime. What is the derivative of x squared? That is going to be 2x, right? So that is the point of my b prime. And I'm going to have that minus f of a, which I'm inputting my a, which is 1. So 1 squared plus 1 times the derivative of a, which is my a prime, which is going to be 0, right? So my second term just goes away because I'm multiplying by 0, and that's why you rarely see this formula that I have here, because you always start from 0 to another value, right? But when you start changing your functions, right? When you start changing your functions, you actually need to apply this definition right here. And the difference between it being an x squared and an x, if you guys see, when I would take the derivative of an x, right? What is the derivative of x? Well, that is just 1. So it doesn't really affect my function, right? It is if I'm multiplying it just by, I'm multiplying it right here just by 1. So that wouldn't really make a difference, right? So that is why here when I have an x squared, the derivative is a 2x, so it actually makes a difference. And that's why we have a different answer. So if we just clean this up just a bit, we're going to bring the 2x to the front, and then we're going to have square root of x to the 4th plus 1, and that is going to be equal to our g prime of x, right? So that is how we're going to start applying the first part of the fundamental theorem of calculus. We're first going to input, we're going to input our upper limit, and then we're going to multiply by the derivative of the upper limit and do the same with the lower limit. And you guys will get the same answers. This is just a more complete definition that I like to use. So, now let's go ahead and do part B, in which they ask us to find the double derivative, right? So the second derivative of g prime, right? So the first part just asked me to find the first part of the fundamental theorem of calculus. If I just were to ask you for the second derivative, I would first have to go through the first part of the fundamental theorem of calculus, which is what I just did, right? This right here was the first part. I can call this right here part 1, right? But then right here, when I ask you to find the second derivative, you actually don't even need to use part 1. All you're going to be doing is just taking an extra derivative. So this looks to me like a product rule that I need to take. I have a function here and I have a function here. So we're just going to bring it back and do our product rule. We won't do another type of second part 1. We never do that, right? So if I ever ask you to find the second derivative and you use part 1 of the fundamental theorem of calculus for the first part, you just take a regular derivative right after. So I chose a kind of difficult derivative here to start off with just because we're already good at derivatives and it's time to just step it up. So let's go ahead and do that. I'm first going to start by rewriting my g prime of x as 2x and x to the 4th plus 1 to the 1/2. And then I'm going to go ahead and derive. So I'm going to get g double prime equal to derivative of the first, which is 2, times the second, which is just x to the 4th plus 1 to the 1/2, plus the derivative of the second, which is 1/2, x to the 4th plus 1 to the negative 1/2, times the derivative of the inside, right? I kind of snuck in the chain rule in there, the derivative of the inside. That is going to be 4x cubed. And then we got to multiply it by the first, which is just 2x, right? So now we're going to go ahead and clean up just a little bit. So we're going to have g double prime of x is going to be 2. I'm going to go ahead and change, well, I'll leave that off for the same step. I'm going to leave it like this. Keep in mind that I don't like fractions of my exponents. But right now I'm cleaning up like my coefficients. So this 2 and this 2 right here are going to cancel. I'm going to bring this 4 to the front. And I'm going to combine this x cubed with this x, giving me an x to the 4th. Right? Yeah. Giving me an x to the 4th. Awesome. So then I'm going to have to bring down this whole negative fraction. I'm going to bring down this negative fraction because I do not like negative exponents. So I'm going to have this to the 1/2, leaving me with a fraction exponent. So I'm going to go ahead and get rid of the fraction exponents all at once. Therefore, giving me that g double prime of x is equal to 2 radical of x squared plus 1 plus 4x to the 4th over radical of x to the 4th plus 1. And I am done. So right there, you guys can see that I simplified it all, and I am going to be done. So now let's go ahead and do some practice problems on the first part of the fundamental theorem of calculus. Just remember, guys, write down this formula that I made. You can call this Junior's equation. Up to you. But it is going to make your life easier when they start changing the equations, right? Because the hardest problem, an example of a very hard practice problem for this would be something where I'm going to write it down here, right? I put functions on either limit, right? So I put like an x squared here, and then I put like a 9x to the 5th. You know, their derivatives, they all matter. So you got to start looking out for that. So I'll leave that off for some practice problems. So now let's go ahead and get to that. See you guys next time.